So energy production part 2, we're talking about nuclear reactors and the moderator specifically. Borna, what does the moderator do?
Slows down the neutrons.
Good. Slows down the neutrons. Luke, why does it slow down the neutrons?
So that it can split the atom into two, otherwise it goes through it.
Good. If it's going too fast, it just goes through the nucleus, so we need to slow them down. So, if you want to stop the reaction, will the moderator stop the reaction? No. You need something that's not just going to slow them down. You need to absorb neutrons. Why do we care about neutrons anyway? Why is this? What is it about neutrons that's so important?
The neutron goes into the, and then it's got one additional neutron, and it's like, can't have that.
Good. So when U-235 splits, it releases 2 or 3 neutrons. These go out and hit more nuclei, which release more neutrons. You get the chain reaction, right? What happens if the chain reaction gets out of control? Boom. Too much heat in too small of a space in too short of a time, and we have explosion, right? We have things melting. This is not good. So we got to keep it, we have to let it go, but we have to keep it moderated. So that's what the moderator is for. If you lower the control rods, so everyone say control rods absorb neutrons.
Control rods absorb neutrons.
Good. It's important to understand. Putting the control rods in stops the reaction. So if you're ever working on a nuclear power plant and they're like, it's getting hot, don't pull the rods out. Put them in.
Couldn't you also just remove the moderator and then the neutrons would be going too fast?
The moderator is usually impossible to remove. So it's like when Fermi built his very first core, his fission core, it was blocks of carbon, graphite, with little corners shaved off, and he put the cubes together, and then he had these pellets of, for him it was plutonium, and they put it like in a hole inside this big graphite block. So to remove the moderator would be impractical, it would be hard. But the control rods, you leave cores.
But if it's water, couldn't you just drain it and then refill it?
Oh yeah, but if you drain the moderator, then that could be bad too.
Why? If they're going too fast to react, then how could a chain reaction occur?
Maybe. I don't know. That seems scary to me.
And the water also acts as like
The water is also acting as a coolant. Yeah.
Is that why the
So that's it seems troublesome.
Yes, that
I see what you're
How
saying.
would we heat it for some
But
reason?
generally we let the moderator slow down the neutrons. That's doing its job. And then the control rods absorb neutrons when we need it to cool down, and then don't absorb neutrons when we want to let it run.
What happens to the absorbed neutrons?
They get absorbed and they're done. They get absorbed in the rod. I think these rods are boron or something. I can't remember. Put your hand if you recognize the name Chernobyl. Everybody knows Chernobyl, right? So apparently, at Chernobyl, bye Allison. Hi Allison, if you're watching this. Everyone say hi to Allison. I've never thought about that. We give each other secret messages, and then when you watch the video, so the control rod comes down, absorbs the neutron, stops the thing, right? So at Chernobyl, apparently, the story is these control rods, they fit into this cylinder in the moderator, and they got corroded. And when things were getting out of hand, and they were like, "Okay, drop the control rods, we'll slow it down," and the control rod went gunk, and it got stuck. It didn't go down there. That's the story. There's a big, like, multi-part miniseries about it. So all this detail, and I started watching it. It was so depressing, I just couldn't watch the rest of it. So I don't know all the details of the story, but there's a lot to it. And the end result is a lot of people died. The reactor core melted down, exploded, rained graphite pieces everywhere, and they brought in the local fire department which many of them were your age. And they also brought in the Army Reserve, which were more people your age. And they had them carry the graphite pretty much unprotected and throw it in a big hole that they dug with some excavators. And all those people died within a very short time. So Chernobyl was bad. There have been other accidents. Do you know the name of any other accidents? Fukushima. So the final reports are coming out from Fukushima now. There are some details, but basically, radioactivity-wise, probably didn't kill anybody, and probably no permanent effects.
Wasn't there that one?
It was very.
Briefly exposed.
Yeah, so the people who were in there,
Yeah.
who actually like were too close. I shouldn't say that. I shouldn't say nobody, but like broader public
Yeah.
world. The effect of it was actually very minimal because the safety mechanisms actually worked, and it was handled the way it was supposed to be handled. It was still scary, but and then there's also 3 Mile Island, which it was scary, but again didn't really have any serious effects.
How would the control rods becoming stuck lead to?
They just didn't fit, and then the reaction is going,
Oh.
so it can't go down the cylinder. Yeah, Eric.
Why do they use U-235, like not on, well, not U-230
So U-238 will fission, but it doesn't release neutrons. So you can fission it, but you have to like have a continual source of neutrons. It's not it won't do a chain reaction.
Is the reaction just doesn't release any neutrons against?
Well, so 238 will fission, but very, very slowly. And it doesn't, you know, when it decays, it doesn't release any neutrons, so it doesn't cause any other atoms to fission. 235 is special in that when it fissions, it does release neutrons, and those hit more. 238 is much, much more common. It'd be way easier for us if 238 could be used, but there's a reason though, probably. Can you think of a reason why 238 is more common than 235? Because it doesn't do that, right? There probably was a bunch of 235 around, you know, when the Earth was first formed. And there was a bunch of nuclear explosions and it's not there anymore, right? Kenta.
You can use plutonium and they don't require moderator rods because they're slower. That's what it says on the package.
Say that one more time.
You can use plutonium,
Yeah.
isotope plutonium,
Yeah.
which you can get from doing like breeder reaction.
Breeder reactor, yeah.
Uranium.
Yeah.
And you can get plutonium, which is slower, so you don't need moderator rods to do the reaction. But plutonium is a lot more toxic, apparently.
Yeah, it's toxic and hard to handle and stuff. Yeah. Yes, and there are, I should say, so this is just a little bit of a different design, and it's got a solid moderator, graphite. This one has water, but these designs are old. So the designs that are coming out now, by the way, Canada is a world leader in designing these. Interesting though, in British Columbia, where we have all this wonderful hydroelectricity, it is illegal to build a nuclear reactor in British Columbia right now. Don't know. Somebody at some point was like, no, I'm not having it. So you can apply for a permit, but they'll tell you you can't because it's illegal. But we think that's going to change. And on the other side of our country, we have people designing these amazing nuclear reactors that are going to save the world. Okay. So here's your reaction. You guys know these, right? Is it always these two products?
No.
No. It's going to be some variation. Like this is 140 and 94. But, or sorry, I should say 54 and 38. But it could be different. It could be 53 and 39, right? It's just kind of random. So it's not always the same products, but of course it always adds up. So heat exchanger, blah, blah, blah. And there's some problems, there's some Kind of practice problems here. Risks, blah, 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 blah. We already talked about that. Okay, solar. It has been said that we don't need to build a fusion reactor because we already have a fusion reactor, but it's not on Earth. Yeah, you can even see it today. It's out there somewhere. And it's dumping on us a daily dose of energy. The average around the Earth, anytime, day or night, is 1,400 watts per square meter. That is enough energy to power everything that humans do, no problem. You don't need even to take up very much space. But there's a problem. The solar panels that we use are fairly inefficient. And it hasn't been adopted very well. You get 1,400 watts per square meter at the outer atmosphere, but on the surface it's more like 1,000 watts per square meter. Why?
Because it gets deflected all the time.
Yeah. Some of it gets absorbed and scattered, some of it gets just reflected back into space. Right? So we don't get all of it. And solar panels are photovoltaics. I have read some designs are getting up to 40%, but if you go out and buy one, you're probably going to be more like 20%. And if it gets dirty and it's not pointed directly at the sun, it goes down from there. And here, it's not very practical because we don't get that much sun. But it's making strides. Hydroelectric is what we have. Luckily for us, and China made that massive Yangtze River Dam. If you want to find the energy of hydroelectric, you have the river comes down, right, and it goes down this penstock, this pipe that goes down to a turbine. It's basically potential energy over time. That's the power that you can get out of the water. You understand? This makes sense? So you have mgh, the mass of the cylinder is the density of the water times the volume of the cylinder. You get that? So you have a, Farham, you know this number?
Yeah.
Okay. You have falling down this cylinder of water. Okay. It's a cylinder because it's a pipe that's going down. And this water is coming down towards this. I'm not drawing it as it is, but it's like a turbine that's going to spin, right? This is just gravitational potential energy, right? By the way, what gets the water up there in the first place?
The sun.
The sun. It's all the sun. The potential energy of this is the energy that you have to take, yeah? And if you want to calculate the power, you just get the potential energy over time. So our power is mgh over T. The mass of the cylinder is the density of water, which is 1 kilogram per liter. Right.
How is the mass of the cylinder the density of water? How is the mass of the cylinder the density of water?
The mass of the sun?
The cylinder.
Oh, well, it's the mass of any cylinder is the density of the stuff times the volume of the cylinder, right? So it's just density of water times the volume. So rho is the density, and you have the volume of the cylinder, and then you have GH, and you have over T. What's the volume of a cylinder? Yeah, it's just the area of the disc times the height of the cylinder, right? So you have the volume of this is pi r squared times h, I guess.
But not the same H.
Is it gonna be the same h? I think it will be the same h.
Only if it's vertical.
Well, actually, the better way to say this h is vt,
Yes.
because the velocity of this times the time will give you the distance that the water moves. In that case, I think they do that here. So yeah, they say delta v over t, and then they say that q is delta v over t, and they make that. I don't know why they use q, but what does your formula booklet say?
It doesn't have that formula.
No.
No.
Okay.
No.
We need to know that?
Yes.
I don't feel like I've never seen that.
I don't feel like learning
Long
it, so.
exam.
Well, you probably don't need to memorize the formula, but you should understand that a hydroelectric dam runs on gravitational potential energy.
They'll be
And so-
learning this in the new syllabus, though. Like,
Don't know that yet.
yeah.
You should know that. You worry about the new syllabus. The old one is hard enough. Okay, so that's hydroelectric, and I realize that you're getting bored, but I'm gonna keep going anyway. Wind. Wind is great, because it just, and you get to pull it out, and you get electricity, and there's no emissions, but it's also not great. Why is it not great? You got these big ugly windmills. The one on Grouse is kind of pretty, but it never turns, so I don't know what it's doing up there. Aesthetics, yeah. I think it's just the tourist attraction part of it. Tell me how you would calculate the potential power coming out of a wind generator. So you need the speed of the wind. What else would you need? Luke knows.
Area of the wind turbine.
The area of the circle.
And its revolutions.
And so if you have the area and the speed of the wind coming through, it's another cylinder, right? So you can use the area of the disk times the velocity of the wind times the time. That's the volume of the cylinder moving through the wind turbine. You get that? Kind of, sorta?
We'll also need row air.
Yeah, so you need the density of the air to get the...
What if a shark uses that as a toothpick?
It's, okay, think about it this way. You have a wind generator. You have air, let's say it's blowing at 20 meters per second. And it hits the windmill. What type of energy do we have? We got kinetic. It's half mv squared, right? Can we ever get all of that energy out of the wind? No. Why not? Yeah, but don't worry about the friction. Could we potentially get all that energy?
No,
Or
this
not?
doesn't
The wind would have to stop
Ah.
after the turbine.
Very good. Let's give a golf clap. The wind would have to stop, and if the wind stops, then the air behind it will pile up, and it will stop turning. So we can't do that. So you're going to have some velocity after the wind generator, right? So it's the half mv squared before minus the half mv squared after. Does that make sense?
Yes.
So the air is going to be slowed down, and it's basically the kinetic energy you take out of the air. That's the potential energy gain that you can have in the wind generator. So you have this like tower with these big blades, right? And they're going around. And so there's a cylinder in front of this, and then there's a cylinder after that. And the one in front is moving with a big V, and the one after is moving with a smaller V.
How do we know what the length of the cylinder cylinder? Is it arbitrary or?
Well, it's tough to go up and stand in front of a wind generator with a big ruler stick and be like, it's 3 meters long. You're not going to do that, right? But it's really easy to measure the speed. And so if you know the speed, you can just do the speed times time, and that will give you the displacement.
Does time cancel out?
Yeah, time's going to cancel out. Yeah. And so you can do the half mv squared over here and the half mv squared over there, and you get the difference, and that's your energy that you can get out of the. And so to get that mass of that column of air, that cylinder, you need the density of the air times the volume of the cylinder, right? So it's just pi r squared times the length of the cylinder, I suppose.
Is the diameter of the cylinder the diameter of the thing?
Yes, the diameter of the cylinder is the diameter, the radius of the radius of the cylinder is the radius of the windmill, wind generator, I
The
should say.
reason why we calculate the volume is just to get the mass so we can do the kinetic energy.
Exactly, yeah. You just calculate the volume and you times it by the density of the air. Do you guys know the density of the air?
Doesn't it change with pressure?
Hold your hands like this, 1 meter, now high, and then in front. That's 1 meter cubed, right? That weighs about a kilogram, a little more. And Jeffrey's right, at different pressure, it's going to be a little more, a little less, it's going to be a little less.
Higher velocity would have higher pressure.
Yes.
So,
Sometimes, it depends. It depends, because sometimes if you have like a heat, it's actually pulling the air in. So it's moving fast, but it's less dense.
yeah, but in this case,
If it's being pushed up against a mountain, it's getting squished, maybe more.
yeah, in this case, it's kind of
In this one, it's probably more because you're getting,
so you gotta take that into account.
you do, yeah. Yeah, so there's questions about the pressure, but they'll just tell you the pressure. Or they'll tell you the density. So this is a Sankey diagram for the wind. So you lose 20% to just turbulence and aerodynamics and stuff. You lose another 40 to friction in turning the blades. And then 5% you lose to electrical things. And you're left with about 30% of the energy. So it gets, this is power, right? It's generating electricity is depressing because you just keep losing stuff. It's like trying to invest for your retirement. You just keep losing. Yes, Jeffrey?
So, 2 questions.
Yeah.
The excess velocity that we have after the
Yeah,
turbine,
yeah.
what category does it go into in those 3 losses in the diagram?
Well, that in the Sankey diagram, it's only, you've already done this calculation. Like the 100 is the difference in these 2. This is not a, we don't count this as a
Okay.
loss.
And the second thing is we calculated on the entire radius, but
Yeah.
it's not the entire radius that just pushes the turbine. So how is that?
No, but that's what you lose. That's that 20% of, you're not going to get all of it.
No,
Right.
like compared to the area that the turbines go around, the blades are very thin. So it's not that entire area that gets pushed.
Yeah, but
Isn't
it
that-
doesn't matter because if the blades were not there, the air would just blow through, right?
Yeah.
So whatever is slowing down the air, that's what the blades get to take. So that's what it is.
Like, I don't understand why the entire volume of the cylinder would turn into kinetic energy that we can get, because
It essentially it doesn't matter because you're just measuring the difference from this cylinder to this cylinder. If it was a turbine of blades that covered the whole thing, it would slow it down more, but it'd probably be less efficient. And then you'd have it hitting and going around and all these kinds of things, right? But you're right to think about that. But because we just do the simple, this is kinetic energy before, kinetic energy after, the difference has to go into the blades. Yeah, Borna?
Aerodynamics
density have to be 0 after 2? Like, does all that have to be converted to
Does the air density have to be?
0 after
No. No.
all the mass doesn't have to like.
The density probably will change. The density here is probably different than the density there.
Why? Shouldn't it be much lower?
Because you're hitting a resistance, and so stuff's getting stretched out. But they'll tell you
It's
that.
not like it's consuming the air.
That's my decision.
No, but it's changing the air, right? It's changing it. So there's these four, and I think you do have this formula in your data booklet. Do you not?
Yes, you do.
Yes, Jeffrey?
So just to clarify the questions, we would be given the initial and the final velocity of the air going through, right?
You might be, or you might be told the current that the thing is producing,
That's
and then you go backwards. I guess. Society demands action. I don't know. That's your job now, is to demand action. Actually, your job is to do the action. That's energy production. All of it. So there's test yourself questions in here, and there's also exam style questions. And there's also, you can look in the past exams and see what kind of questions they actually put on the exam. I might start there if you want to be expeditious about it. I'm going to give you next class in its entirety to just do these problems. And I'll be here and we can practice them. You want to do paper 3?
We'd like practice paper 3. I don't think we have touched on specific stuff.
Do you want to like take a whole class and just do a paper 3?
Yeah.
Yeah, like everybody together?
Yeah.
What's the time limit for the paper 3?
No idea.
together or by ourselves?
Well, like by yourselves, but maybe together. I don't know. Yeah, we can look at that too. How many classes do we have left?
Like
Are you serious?
We got no time.
Whoa.
T minus like 16.
Oh my goodness. 20, April
25th.
25?
Yeah.
Yes.
Yeah, 25
Wow.
paper 1 and 3.
Why is it so early?